Okay, let's just call this a little thought experiment. Let's say we have a target, a square target. It's an unconventional shape for a target. Nonetheless, this square is 1 by 1 by 1, so 1 on each side. Now, for those of you who know, to get the area of this, we multiply the width by the height, which gives us 1. So we'll say it's 1 meter by 1 meter, so this is 1 meter squared. Now we have a shooter who happens to be a very random shooter. Random in the most literal sense. His shot could end up literally anywhere within this square. But here's the important thing. There is a 100% chance that it will end up inside the square and a 0% chance it will be outside. Now, if we were to divide this square up into sections, say we went 0.2 meters in from this side and drew a line, we'd have a little section here which would have an area of 0.2 meters square. Now, if our shooter shoots completely randomly, what is the percentage that he will hit inside this area? Let's call this area A. And we can denote the probability that the bullet will land in A as such. So our question is, what is the probability that the bullet will hit A? Now, as I've said before, the area of this is equal to 0.2. So that means the rest of this area would be 1, because you know the square's area is 1. Take away 0.2 and we're left with 0.8. So this area is 0.8. Okay, so if this area is 0.2, we can work out the percentage that this area takes up of this whole square. We can say what is the area of this as a percent of the whole square? It's 0.2 over 1, which is 20%. Now, if the area of this section is 20% of the total area, and then the bullet can hit anywhere within this square with an even chance, just as likely that it hit anywhere as it is anywhere else, then I think it's fair to say that there is a 20% chance that the shooter will hit inside A. We can also express that as a decimal or as a fraction, a 20 out of 100 chance. Now, we could pretend there's prizes for this. If you land in A, you get paid $1. And why don't we make another little area? Let's call it area B. Now, area B is going to overlap with area A. Let me just get some more colors. So we've got area B. And all right, this isn't to scale, but take my word for it. This is 0.1 meters long, this section, which means the area here is 0.1, because it's, again, 0.1 multiplied by 1, height times width, all that stuff. So area equals, and just a reminder up here, area equals 0.2. Okay, now area B's in the mix. So we had probability of hitting in area A is equal to 0.2 or 20%. And using the same logic before, probability of hitting in area B is equal to 0.1, which is 10%, because area B takes up 1/10 of the entire area. Now, I said before there's prizes. Let's say you get $1 for hitting in area A, hit A, prize $1, hit B, we'll call it $2. Now, say you're running this game at a carnival, you want to work out what to charge people to play it. You might be interested in what's the probability of hitting. Sorry, let me rewrite this. Well, let's not worry about the probability for a sec. Just say if they hit A and B, so if they hit in here, they're paid $3. Seems fair, right? Add 1 to 2, you get 3. Sounds good. So as the game operator, you might be interested in what is the probability of A and B. Because if you're going to charge people for this, you want to make a profit. So to get an idea of what that price that you should be charging people is, you should know what you stand to lose. So what is this? Well, I mean, that's easy. It's the probability of getting something in this tiny little box, which we know is 0.2 meters wide and 0.1 meters tall. And we know how to work out area. We multiply height by width. So 0.2 times 0.1 is equal to 0.02. If you don't believe me, check that on a calculator, which is equal to 2%. So, following the same logic we had before, the answer to this, probability of hitting in P and A and B, is 2%. Okay, so the purpose of all of this was to help you understand how you can visualize probabilities as areas. Probabilities as, areas. And that's going to come in handy later.